a brand name kettle here, all branded up, just like the football team likes. And we're going to boil some water. So heating water at Nelson. How much heat is needed to raise the temperature of 2.20 kilograms of water? Now, 2.20 kilograms. Not that it's relevant for this question. How many liters is that? What is it? 2.2 happens to be. Look at that. 2.20 liters of pure water. It's not relevant for us right now, but it's a good piece of trivia to hold on to, okay, for unit conversions. From 20 degrees Celsius to the boiling point. Now, if it starts at 20 degrees Celsius, is this the initial temperature or the final temperature? Initial. So the way we're going to indicate that is T1 for water, T1W. Now, I know we're only dealing with water right now, but if you sneak a peek ahead, can you see? Anybody know their Minecraft well enough to know what I'm putting into water? That is iron. That's iron. You can't tell because it's black and white. We're going to put iron into water, okay? So if we have to keep track of water and iron in the future, we're going to keep track of it in the subscripts, okay? So I'm starting now. It is the OG iron from I'm rocking back in the day. Okay?
My day?
Yeah, back in the day. All right. Now, when we get up to the boiling point, remember, we were good at this from kinematics. What's the implicit information here? If you're getting to a boiling point of pure water, what is it? Yep.
100 degrees Celsius.
Yeah, 100 degrees. So T2W, 100. You know what? Moving forward, if that implicit information for water comes up, let's just say that it's 4 significant figures, okay? 100.0 degrees Celsius. If that implicit information, we'll go with 4 significant figures. If at some point in the textbook it says 100.00 degrees Celsius, 5 significant figures. More for everybody, okay? That's fine. All right. Now, how much of this stuff do we have? Oh, yeah. So let's write out our givens. The mass of water that's in this brand name kettle is 2.20 kilograms. The initial temperature for this water is 20.0 degrees Celsius. The final temperature for this water, 100.0 degrees Celsius. And as I go to calculate delta EH, how much heat energy I had to add to this water, delta EH is equal to M times heat capacity of water, remember it's specific to that substance, times delta T. What information am I missing? Yep. Yeah, the heat capacity. So I'd have to go look that up because chances are you don't have it memorized. And so I would go look it up on a table of values. Hey, look here. I wrote it down on a table of values. It's 4.18 times 10 to the power of 3 joules per kilogram degrees Celsius. So I'm going to write it down as my givens. You'll always be allowed to look that up, or it'll be provided for you in a table of values. 4.18 times 10 to the power of 3 joules per kilogram degrees Celsius. You never have to memorize your heat capacities with me, okay? You might find somebody that makes you memorize heat capacities. I think that that's a useless expenditure of my brain space. All right, so I sub in my values. Remember, in chemistry, they'll have you do mass in grams, but in chemistry, their heat capacities will be in joules per gram degree Celsius. Okay, so that'll be the difference. Remember, I did say we're speaking the same language, but slightly different accent. That'll be the difference, okay? They'll use their heat capacities with grams in the denominator of that unit, and that'll shift the exponent on the 10 to the power of. Anyway, I sub in my values. 2.20 times 10 to the power, oh no, it's not times 10 to the power of, it's just 2.20 kilograms, isn't it? 2.20 kilograms times 4.18 times 10 to the power of 3 joules per kilogram degrees Celsius times, remember, delta T means T2 water minus T1 water. So I got to be able to decode the math to be 100 degrees Celsius minus 20 degrees Celsius. I pop that into the calculator. How much energy are we using to raise this this water up? Yes, sir.
80.
80. I don't think so. That's how much temperature, but it's not how much energy. You're right. There's a temperature change. Yeah.
735,680.
Oh, by golly. Say that again. 735,000.
680.
680. Wow. Joules. Now, does anybody here remember how much energy they took to climb to the top of the stairs a few days ago?
600 and something.
600 and something? Yeah. So a few days ago, we ran up the stairs. We ran up the stairs from the bottom of the stairs up to the top of the stairs, and we calculated how much gravitational potential energy we had at the top of the stairs based on our body mass and how high the staircase was. And a lot of people ended up having like, what did it end up being, like 700 joules or something like that? Does that sound about right in the neighborhood? Yeah, I'll do the math. Look, let's just say that we went up 3.5 meters. How high was the staircase? 3.5 meters sound good? Let's say 3.5 meters times 9.81 times, let's just say somebody was a 70 kilogram student. All right. So 2,403 joules. Yeah? That seems okay.
How long did it take?
So 2,403 joules for somebody to climb the stairs. We're talking about 736,000 joules to boil a kettle of water. You see the scale difference there? The reason why kettles take so long to boil the water? That's a lot of energy. We talked about, could you, with your energy capacity, power an appliance? It would take a lot of energy for you to boil a cup of water. Like to hook you up to a pedaling machine and have you be the generator, it would take a long time for you to boil a pot of water, for sure. I could round this guy off to 3 sig figs. 7.36 times 10 to the power of 5 joules. This is like more than 100 times the amount of energy that you put out to climb the stairs. In other words, you'd have to climb 100 stories to boil a pot of water. That's crazy. That's a big energy differential, right? And it really puts in perspective how powerful these appliances are in our kitchens. You know, if you run 3 kettles at the same time in your kitchen, I bet you most of our houses would pop a fuse. You have to go fix the breaker in the basement or something, right? Reset the breaker. This is a lot of energy. It really is. Let's think about this. What that means is if I have 2 glasses of water and they're out in the sun, you know that it would take more energy to heat up the large amount of water than the small amount of water, right? That makes sense. Another thing, although that's not exactly what this picture is about, another thing is that it must take a lot of water, or it must take a lot of energy to evaporate the water. And it's a good thing that we live near a giant nuclear furnace, because our sun is sending tons of energy to us all the time. It's like we're spoiled rich kids. We're rich with energy. We got to figure out how to harness it, but there's a ton of energy coming to us all the time. We know that. It's just this wealth of energy. And it's not a wealth that we don't spend. We do spend the energy, don't get me wrong. Like all the wind power, all the tidal power, everything is driving our systems, right? Photosynthesis, we're eating the energy, right? Let's think about this. Iron. Here's my Minecraft OG iron. And I put my iron into water. Remember we said once before that we weren't always going to put the same substance into itself? So now we've got iron, and I want my iron. I'm going to say T1 for the iron, T1I, is equal to 100 degrees Celsius. Okay? 100 degrees Celsius iron. I know that the heat energy for that iron would be calculated as the mass of the iron times the heat capacity of the iron times how much temperature, what the temperature is for that iron at that moment in time. Notice that I'm not talking about the change in heat. I'm just saying I could calculate how much heat it has. It owns that much heat energy. It owns that many joules of heat. The water, on the other hand, if the water had a temperature, let's just say T1W, of 40.0 degrees Celsius, I could say that the heat energy for the water is equal to the mass of the water plus the heat capacity of water, times the heat capacity of water times the temperature of that water, T1W. What we did before was we put these things together, we called it a mixture. Now, when you're mixing a beaker of water with another beaker of water, it's obvious that it's a mixture. But in physics, when you put something into another thing, we call it a mixture. If this was Cheerios and we put it into milk, you'd call it a mixture. It doesn't matter that it's heterogeneous or homogeneous. It's a mixture when you slosh one thing into another thing. Okay? So this is a mixture. Now, what I would say is for sure, doesn't this iron lose energy to the water? So I'd say E lost. It doesn't destroy the energy, but the energy is lost to the water. We know that. My own sister one time took a pot off the stove and she didn't want to put it down on the countertop, so she put it into a sink full of water. Now that damaged the pot. You shouldn't do that. It'll contract too quickly, it'll damage the bottom of the pot. But she took iron and she put it into a sink full of water. A blacksmith might take horseshoes, and after making them, however blacksmiths make them, they get quite hot, and then they would dip it into water. This is all stuff that we can imagine, right? The iron loses the heat, the water gains the heat. The heat is not destroyed. It's the same amount of heat. Everybody agree on this one? So we say, all right, EH total is going to be EHI plus EHW. The total heat of the iron plus the total heat of the water. Those two add up to give us the total in here. And we can make little statements like iron, spelling. Iron will lose energy as it cools. No doubt about it. And we call that a heat exchange. Water will gain energy but no energy is destroyed. That's an important but. No energy gets destroyed. It's just an exchange of energy, right? And you know that this is going to be true. Now, we said before the heat capacity of iron is like a tenth of the heat capacity of water. So you notice this. If you put a block of iron into water, does the water heat up or does the water's temperature rise very much? No, because it's got a high heat capacity. That's something that I want to make sure that we get really clearly, okay? In terms of, we're going to wrap this up in just a second, okay? In terms of how we keep a closed system, this is a thermos. You want to keep the lid tight because we're going to do an experiment at some point. This is some things we want to think about. Keep particles from getting in and out. We want to have an outer cover, keeps radiation from entering. And when I say radiation, we could be talking about like solar radiation. A good thermos has a vacuum layer in between the outer layers, and that omits the possibility of vibration energy.
Omits?
Eliminates? You like that better?
Mm.
Transmitting in by conduction. If you like eliminates better, that's fine.
I was just wondering if that one
Okay.
is.
And then a really good one will have an interior silvered layer that reflects radiated heat back into the container. That would be the ideal thermos. Something that does all of those things. Keeps the particles from getting in and out, so it's physically closed. Keeps radiation from entering. Eliminates the possibility of vibration energy transfer, so that's like heating by conduction. And reflects radiation back into the container so that hot substances don't just radiate out their thermal energy. That would be a great thermos.